start lecture 33. And we will continue our discussion on kinetics of corrosion. Now, in the last lecture, at the end, we have come to a situation where if we consider a single Hubsel redox reaction O plus Ne equal to R, and then we try to see the equilibrium condition, which is K C O, concentration of O, equal to K A, concentration of R, and then we have taken logarithm on both sides, ln K C plus ln C O equal to ln K A plus ln C R, and after distribution we are getting ln K A plus ln 1 by K C equal to ln C 0 by C R, and we also know that E minus E 0 equal to R T by N F ln C O C R, which is the concentration of ox divided by concentration of R, and then we can put this one with reference to potential E minus E 0 N F R T. Now, if we differentiate both the sides with reference to E potential, since K A as well as K C both are potential dependent, so then we get D and if we consider that N is 1, that means for this particular reaction the number of electrons participating to reduce one oxidant to one atom of one particular ion of oxidant is going to the reductant in case of Mn plus Ne equal to M is basically one ion of Mn plus we are reducing to M, which is reductant. So, then this N goes to 1, we can write R T by F D D E ln K A plus R T by F, and this side definitely when we are doing D E, then this would become, this is constant, so it will go out, since this is taking place, this reaction is taking place at a constant temperature, and this is 1 Faraday which is constant, this is a constant. So, it would become 1. So, this E, so del E del E del E of E del E of E is equal to 1. So, this goes to 1. So, then would be equal to 1. Now, this quantity and this quantity, this is called alpha, which is the cathodic or reducive symmetry factor. And this we can term it as alpha prime, which is oxidative symmetry factor. Now, if I try to look at this quantity, this is nothing but the slope of 1 by K C for a particular plot of K C and E. So, if we see this quantity only, R T, I am just considering d e ln 1 by K C. If I try to look at this, then we have already noticed that if potential is this and K C is this. So, this would be like variation would be like this, because once K C increases, potential drops from the standard equilibrium potential, which is cathodic polarization. So, 1 by K C would be just opposite to it. So, 1 by K C, and the slope of that point, which is so d e ln 1 by K C. So, if we take log of this and then try to plot them again, and then we have to take the logarithm of that 1 by K C, and then we differentiate with reference to with respect to E. Then this quantity with the multiplication factor R T by F is nothing but alpha. Reducive symmetry factor, and of course, the other part, this is the oxidated symmetry factor, which is talking about the oxidation K A value, which is the equilibrium, the rate constant. Now, we have to have some sort of clear cut picture on this alpha, which is the symmetry factor, which we can explain by drawing some schematics. Let us say if alpha equal to 0.5, and if we consider two planes, let us say these are the two planes and this is distance, this is g axis, this is IHP, this is OHP. Then initially they were at the same plane because they are at equilibrium, and then we have the energy axis distribution. Energy distribution is like this, and here it is R and here it is ox or oxidant, metal iron surface and metal surface. Now, if we see that oxidation process becomes faster, then there will be change in the activation energy, as we have noticed earlier. So, the new position of the activation barrier would be this one. So, you could see that activation energy is going down for the oxidation process. This is oxidation process or IA. So, the IA increases, and for the reduction process the activation energy increases from the earlier one. This is delta G C and this is delta G A. And when it happens symmetrically, that means maintaining that equal distribution of the total polarization or over voltage. If this is my over voltage value neta, so then in this case m n plus plus n e equal to m for this particular half cell reaction, the free energy change would be n f neta. This is my free energy change due to polarization, and of course, is this the over voltage in volt. So, out of that alpha, this amount will be the amount which will be the change in activation energy for anodic side or delta G A, and then the rest of that particular fraction 1 minus alpha n f neta would be the change in activation energy for cathodic side, which will lead to a change in delta G C. Now, since alpha is 0.5, so the contribution of this total over voltage and thus the change in free energy towards this activation energy would be equal. And in this case, if you see this, so this arm and this arm both are equal. That suggests that contribution of the total over voltage or total energy change, which is this one, would be this fraction and this fraction. And now you need to know that what is that free energy change due to over voltage. This is the amount of free energy change for over voltage, which is equal to n f neta. And interestingly, if you see this, this was the initial free energy when both I A and I C were equal. Now, after this distribution, when I A is higher than I C in this particular situation, you could see that del d G C would be equal to delta G star, which is this one, this is delta G star plus, and if we consider this to be alpha f neta. So, this becomes alpha n f neta, and delta G, because this height plus this one is basically constituting delta G C, and whereas delta G A would be equal to delta G star. So, this amount plus this amount minus this amount. So, delta G star minus n f neta plus alpha n f neta. So, then it becomes delta G star minus 1 minus alpha n f neta. Now, you could see that this value is greater than delta G A. Hence, it would lead to I A greater than I C. We are taking mod because we have assumed that this is a negative current, means the flow is opposite to the anodic current. Now, this is the situation when alpha is equal to 0.5. So, that means the contribution of this over voltage and finally, the contribution of free energy change towards activation energy of cathodic side, anodic side, both are equal. Now, there could be a situation where alpha is less than 0.5. The situation can be predicted in this fashion. This is also, let us say, distance, this is OHP and this is IHP. Now, I can initially I have a situation like this. This is on the same plane, and then if we have a situation, same situation, that I A is increasing. Now, you could see that alpha is less than 0.5, since this part is alpha n f neta. And interestingly, if we see the expression for alpha, is this one. So, let me write down again, which is R T by F d d E ln 1 by K C equal to alpha, which is reducive symmetry factor. Now, we can have a situation when we have alpha greater than 0.5, that case the plot would look like, in this case one more thing, see now this is my total free energy change, and out of that a small fraction, because alpha is less, the small fraction is contributing to the activation energy for delta G C, whereas similar way we can have activation energy change for anodic side. But if we see this arm, these two arms and this arm from this point, this arm is smaller than this and this is equal to this total value, because they are parallel planes, this is parallel to this. So, that is what the contribution would be, this much towards delta G C, and the equation would be similar like this, and the contribution of this one would give us the same formula, which is delta G C minus 1 minus alpha into N F neta. This is the situation when alpha is less than 0.5. Now, we can have greater than 0.5, this is IHP, OHP distance, so the slope of this line would be steeper, since alpha is greater than 0.5, and then if we have the similar variation in anodic current density and cathodic current density, that means the activation energy for the anodic side would decrease, then you can see that this becomes my alpha N F neta and this becomes my alpha 1 minus alpha N F neta, and you could see that these two arms, this arm and this arm, the ratio is greater than 0.5, which is alpha. So, we could see that how alpha changes the slope of these two free energy lines. One is from the R to the activation energy, another one is aux to the activation energy peak. So, these two lines are changing because of this variation in symmetry factor, but in our discussion we would consider alpha to be 0.5. Now, as we have seen before, let us get back to this particular plot. This particular plot. So, if we see that we have seen how the plot pattern changes if we would like to get preferably anodic reaction and preferably cathodic reactions. Let us consider that particular situation. Now, here we are considering alpha to be 0.5 and now we are seeing the change in free energy plot. Now, here initially the free energy plot was like this, which was on the same line, and it was G is same for these 2 points. Now, we are having preferably anodic reactions. So, I am having a change in my free energy plots, and this is m, this is m n plus, this is distance, and this part is IHP, this is OHP, and you could see that the total change in free energy is, after this preferable I A and preferable I C, depending on whether in this case, in this particular plot, we are getting preferably the anodic reactions, that means the rate of anodic reaction is increasing as compared to the backward reaction, which is rate of cathodic reaction, and this is the total over voltage, and now the free energy change would be N F neta, and out of that, if we consider this to be alpha N F neta, and this part would be then 1 minus alpha N F neta. So, then accordingly we can calculate. Now, initially this was my free energy, where when delta G equal to delta G star, that activation energy, that time I A equal to I C equal to I 0. Now, interestingly, before we analyze this part, we need to understand one more issue. The issue is, if we try to see the same equation, which is R 1 R C equal to K C concentration of ox and R A equal to K A concentration of R. Now, this R can be converted to current density by doing the simple formula, which is I C by N F equal to K C C 0, and here it will be I A N F equal to K A C R, and when I C equal to I A, then we have I 0, but if I C is equal to not equal to I A, then there will be a net current flow, which I can write in terms of I applied, which is I C minus I A equal to K C C 0 minus K A C R. This is the net with multiplication factor N F, because I have to consider I C equal to N F K C 0 as well as I A equal to N F K A C R. Now, I can also go back to this alpha. Now, I know that R T N F d d E ln 1 by K C equal to alpha, and here I have put N because we are considering this reaction. So, the number of electrons is basically N. Now, if I integrate this, so d ln 1 by K C equal to alpha since these are all constants, this entire part is constant. So, we are taking it out from integration sign. So, this becomes, and now we have to see the limit. Now, when we have polarization because of that net current flow, either it can go to positive side or negative side. So, now if E 0 is basically my initial equilibrium potential and E is basically the initial equilibrium potential, and this is the final potential after polarization. So, then this should be E0 E, and when E equal to E0, my Kc should be equal to Kc0, and similarly I can put this is Kc0 and this is Kc. So, these are two limits, then I would get ln Kc0 by Kc equal to Nf alpha divided by RT E minus E0. Similarly, I can have this relation for the oxidative symmetry factor. We can also find out the limits. We can write it in this fashion, d ln Ka equal to Nf 1 minus alpha by RT d. Here also the limit would be same. So, this is this, and here it would be Ka 0 and Ka when E equal to E0, Kc equal to Kc0. So, I would get ln Kc 1 minus alpha RT E minus E0. This is oxidative, and another case ln K0 here it would be if we say this should be Ka. So, this would be Ka0, and this is Kc0 by Kc equal to Nf alpha by RT E minus E0. Now, I can write it as ln Ka or Ka equal to exponential Nf 1 minus alpha E minus E0 divided by RT, and here in this side Kc0 or Kc would be equal to Kc0 exponential minus Nf alpha is 0. Now, interestingly, if we consider that I applied equal to K C of oxidant minus Ka concentration of reductant, then if we put those equations, so I get Kc0 exponential minus Nf alpha E minus E0 by RT minus Ka0 exponential, of course, there would be concentration part also, this is Cr minus NF 1 minus, it should be plus E minus E0 by RT. I am just putting this formulas here. I am replacing this Kc and K0. Now, if we assume that C0 and Cr are equal, these concentrations are equal, that means whatever number of ions are forming on the outermost layer is equal to the number of atoms that are coming out. So, if we have this situation, then of course, when E equal to E0, K C equal to K A 0. This is the condition. So, then I can replace this C part in both the sides. It will be simply K0. This is the new formula I am getting. Now, this is nothing but a Buttler-Volmer equation. This equation is called Buttler-Volmer equation. And this is coming from the rate of flow of charges, those metal ions to the inner surface, or the metal from the inner to outer surface or outer Helmholtz layer, and we are considering the activation jump of those ions as well as atoms. So, the Buttler-Volmer equation actually relates important parameters of electrochemistry. One is Faraday current, which is I applied, then it relates to the electrode potential, then it relates to concentration of reactants and product. So, you can consider either M or Mn plus, depending on the reaction you are considering, whether oxidation or reduction. So, all four are connected. Now, this condition is subjected to a situation when I equal to I0 equal to IA and I applied is equal to 0. The net current flow is 0. So, when we have two current density, this is IC, this is IA, they are of the same magnitude, but flowing opposite, then there will be no net current flow in the circuit. So, in that situation, the concentration of this reactant as well as product, or concentration of oxidant and reductant, both are same, and that time we have gotten this particular relation. Now, when it actually polarized, that time this concentration may change depending on whether it is activation polarization or concentration polarization. So, we would look into that part little later, but for the time being, now we see that this Buttler-Volmer equation has a correlation, has a relation between Faraday current, electrode potential and concentration of reactant and product, and from this reaction we can actually derive Nernst equation too. Now, before I conclude, I would like to say that when we have this particular relation, I can equate it K0 and then I can write K0 here also. So, in lecture 33, we need to have a modification. Since I applied is equal to IC minus IA, then with this we need to multiply Nf, and here also Nf is to be multiplied. Since I c by Nf equal to R c and I a by Nf equal to R a. So, the only small change, there should be Nf term added to this, and that becomes my Buttler-Volmer equation. Thank you.